All right, today we're going to tear into a classic physics problem, one of those that looks really intimidating at first. It's got spinning disks, a spring, a whole lot of motion. But trust me, we're going to break it down step by step, and I'll show you a super powerful way to look at it that makes the whole thing click.
Okay, so this beast comes from Irodov's famous problem book. It's number 1.199, and it has a reputation for being a real head-scratcher. And you can see why. It's not just one concept. It's a mashup of rotation, linear motion, springs, and energy, all happening at the same time. So here's the scenario. You've got two identical disks on a frictionless surface tied together by a relaxed spring. Then, bam! You give one of them a sharp kick sideways. Now the whole setup is not just sliding, it's also spinning, and the spring is stretching out. The big question is, what is the absolute maximum that spring is going to stretch? It's that combination of moving, spinning, and stretching that can make your brain hurt.
Now, your first instinct might be to reach for F equals ma and try to calculate all the forces and accelerations. You can do that, but it's the long way home. It gets incredibly messy really fast. Instead, we're going to be smart about it. We're going to pull out the big guns, the most powerful tools in all of mechanics, the conservation laws.
These three are your absolute best friends for problems like this. Conservation of linear momentum, angular momentum, and mechanical energy. You know, whenever you see a system of things interacting with each other, your first thought should always be, hey, can I use one of these? They let us totally ignore the complicated internal forces and just compare the beginning state to the end state. It's like a physics magic trick.
And here is the clue that tells us we can use them. The problem says it's on a smooth, horizontal plane. That's not just fluff. Those words are critical. Smooth means no friction. Horizontal means gravity and the normal force cancel each other out. So what does that leave us with? No net external forces and no net external torques on our two-disk and spring system. And that, my friends, is our green light. It means all three of our conservation laws are good to go.
Okay, now for the part that turns this messy problem into something elegant. It's all about perspective. Instead of watching this chaotic system from a fixed spot in the lab, we're going to use a little trick. We're going to jump into a special moving viewpoint, a secret weapon for problems just like this.
And this right here shows you why it's so powerful. From the outside, in the lab frame, you see this messy combination of the whole system sliding across the plane while also spinning and oscillating. It's a headache to track. But if you imagine riding along with the system's center of mass, all that sliding motion just disappears. From that point of view, the center of the system isn't moving at all. All you see is a clean, simple, symmetrical rotation of two disks around a fixed point. See how much easier that is to think about? So this center of mass frame is our secret weapon. By choosing to analyze the problem from this perspective, we've basically separated the motion of the system from the motion within the system. We can ignore the boring part, the whole thing just sliding, and focus on the interesting physics, the spinning and the stretching.
So, before we can use this frame, we need to know how fast it's moving. It's super simple. The total initial momentum is just the mass of the one disk we kicked, so m times v0. The total mass of the system is, well, two disks, so 2m. The velocity of the center of mass is just total momentum divided by total mass, which gives us v0 by 2. And because there are no external forces, that velocity never ever changes.
All right, we've picked our toolkit, we've chosen our simplified point of view. Now it's time to actually apply our other two conservation laws, angular momentum and energy, inside this nice, clean center of mass frame.
Now here's a really important piece of intuition. Think about it. What does maximum elongation actually mean? It's that one specific moment in time when the spring has stretched as far as it's going to go. For that to happen, the disks have to momentarily stop moving away from each other, right? All of their motion at that instant is purely sideways or tangential as they rotate. Their outward radial velocity is 0. That's the key moment we're going to analyze.
First up, let's use conservation of angular momentum. Remember, we already established there are no external torques on our system. That means the total angular momentum about the center of mass has to be the exact same at the beginning as it is at the moment of maximum stretch, and at every other moment for that matter.
So let's calculate it. Right at the start, in our CM frame, each disk is a distance L0 by 2 from the center and is moving at a speed of V0 by 2. The angular momentum for one disk is its mass times its speed times its distance from the center. Since we have two identical disks moving symmetrically, we just add them up.
which gives us a total initial angular momentum of m times v0 times L0 by 2. And that value is now locked in. It's a constant for the entire problem.
Next up, our other powerhouse tool, energy conservation. This is another spot where students often trip up. They might forget a term or use the wrong velocity. But since we have no friction, the total mechanical energy of the system is also conserved. So let's write down the energy at the start and the energy at that moment of maximum stretch.
Let's look at our energy budget. At the very beginning, in the CM frame, the spring is relaxed, so there's zero potential energy. It's all kinetic energy from those two moving disks. Then, at our final state of maximum stretch, where is that energy gone? Well, the disks are still moving, so there's still some rotational kinetic energy. But now, a big chunk of that initial energy has been converted and is being stored in the stretched spring as potential energy.
And we can write that energy balance as an equation. On one side, we have the initial energy, two disks, each with kinetic energy of 1/2 mv squared, where v is v0 over 2. On the other side, that has to equal the final energy, which is the sum of the final kinetic energy of rotation plus the new potential energy in the spring, 1/2 times kappa times delta L max squared. So now, we've done it. We have one equation from angular momentum and a second one from energy. We're in the home stretch.
So, the hard physics thinking is done. We've set up two really powerful equations that describe our system perfectly. Now, all that's left is to do a little bit of algebra to mash them together and pull out the one variable we actually care about, that maximum elongation.
But hold on. The problem gives us one last gift, a little hint tucked away in the wording. It says the elongation is considerably less than unity. That's just fancy physics talk for the spring only stretches a tiny bit compared to its original length. And this little piece of information is going to save us from some really nasty algebra.
So, here's how that hint helps us. Since the stretch is really small, the final length of the spring is basically the same as its initial length. This makes our angular momentum equation way simpler. It lets us easily find the final speed of the disks, and then we can plug that into our energy equation and solve directly for the stretch. It's a fantastic shortcut.
And voila, here is our answer. The maximum stretch is approximately the mass times the initial velocity squared, all divided by the spring stiffness times the initial length. And you should always stop and ask, does this make sense? Well, yeah. If you kick it harder or the disks are heavier, it stretches more. If the spring is stiffer or longer to begin with, it stretches less. It passes the sanity check perfectly.
Look, getting the right formula is cool, but what's way more important is the method we use to get here. Because this strategy, it's not just for this one problem. You can use it to solve a ton of other tough mechanics problems. So let's just quickly recap the game plan. I want you to burn this four-step method into your brain. 1. Define your system and check for outside forces. 2. If there aren't any, grab your conservation laws. 3. Ask yourself, is there a smarter reference frame, like the center of mass frame, that makes the problem simpler? And 4. Apply those laws and just crunch the numbers. This is your master key for unlocking these kinds of problems.
So I'll just leave you with this to think about. What about two asteroids colliding in space, or a figure skater pulling in her arms to spin faster, or planets orbiting a star? All these seemingly different, complicated problems can be cracked open using this exact same strategy. So next time you see one, don't panic. Just remember the toolkit.